Okay, thank you. Thank you, Hüseyin. We can now listen to you.
Hocam, again, hello everyone. I'm Hüseyin. Greetings from Adana, and today my presentation will be about 2D simulation of a vertical wind axis turbine using moving reference frame technique in OpenFOAM. So I knew that all the previous presenters were going to talk about wind turbines, wind energy in detail. So I will focus mostly on the use of Truba server and a little bit to OpenFOAM, and I will do an hands-on demo, hopefully. So first, I will start briefly with wind turbines, vertical versus horizontal axis wind turbines, a comparison. And I will, in a single slide, talk about simulating rotating geometries in CFD. And then moving on to the method section, I will briefly talk about OpenFOAM and explain the moving reference frame technique, again, very briefly. Then we will move on to the demonstration. We will access the Truba server. I will present the details of our case study. I will show the OpenFOAM case structure, and finally we will move on to the simulation. And we will discuss the results and conclude finally. Okay, let's start with the introduction. As you know, wind turbines are mainly separated into two categories: horizontal axis and vertical axis wind turbines. Vertical axis turbines have some various types: Savonius, Darius, and Aish-Rotor. If you compare them, you are going to see that horizontal axis turbines are mostly suitable for commercial applications, like you are most likely going to see them in a large power plant. But vertical axis turbines are mostly used in domestic applications in small scale. For example, they are put on the rooftops of the buildings. Horizontal axis turbines has higher aerodynamic efficiency, but on the contrary, vertical axis turbines has a lower investment cost per megawatt. Manufacturing of horizontal axis turbines are complex. For example, they require yaw control, but vertical axis are simpler. And horizontal axis turbines generate less noise per megawatt compared to vertical axis. So how to simulate rotating geometries in CFD? Ata has explained the sliding mesh or alternating mesh, arbitrary mesh interface technique in detail. And also we have the moving reference frame technique. If we compare them, in the first one, in the sliding mesh interface technique, geometry is physically rotated. But in the moving reference frame technique, governing equations are manipulated, especially the momentum equation. So you can run it in a steady state. But our sliding mesh technique is strictly unsteady, and it requires very small time steps. Non-conforming cell interface require complex treatment, as you can see here. But MRF doesn't have such a numerical problem. SMI is good for highly transient physics, especially for wind turbine simulations, and MRF handles them poorly. It is difficult to set a good initial condition for SMI. It requires many steps until convergence. Again, MRF does not have such a problem. But at the end of the day, SMI is higher fidelity, often used as the primary technique, whereas MRF is mostly used to obtain an initial condition for SMI. Briefly, OpenFOAM is more than a solver. It is a CFD toolbox. So it has mesh generation tools, mesh manipulation tools. It can convert mesh files between another one. It can decompose the domain. It has many useful features, such as, for example, force calculation, field probing already coded in. Many algorithms, schemes, and turbulence models, boundary conditions are already available. Advanced features from cutting-edge research are quickly packed in the new versions, such as dynamic mesh refinement, moving and morphing meshes, synthetic eddy models, and so on. And there are much more to OpenFOAM if you really dive into it. It is open source, it is widely adopted, it is continuously enriched by the active community. A great environment to learn CFD. So in OpenFOAM, you can see the code with your eye. You can run it, you can get a result, then you can modify the code, you can run it again and see how your modification effectively affected the result. It is a finite volume based code. It is built on incompressible algorithms, in contrary to SU2, which is an compressible solver by heart. So it mainly uses simple and piezo algorithms for pressure velocity coupling. It has MPI based parallel capability. It has two main branches. Professor Uzol also mentioned this, and foundation and ESI versions, but they are very similar to each other. You can use any of them. Downside is it has a steep learning curve, so there are no good graphical user interface. It requires Linux knowledge, and it may be intimidating to new users. But I would like to show you how this turbulent kinetic energy equation is coded in OpenFOAM. You can see the actual equation here. And on the right-hand side, you can see how it is coded in OpenFOAM. So everything is really very intuitional, as you can see. For example, from the finite volume FVM namespace, you can directly use the DDT function for time derivation, time differentiation of K, and so on. The divergence is div, Laplacian is Laplacian. So you can write your solver, your own solver, as if you were writing the equations by your hand. So what about the moving reference frame? So moving reference frame is a technique that can run in steady state. So it is kind of a difficult thing to grasp. So first you define a rotating axis of rotation. For the MRF zone, within the solution domain, you define a small zone which rotates actually. For each cell in the MRF zone, you define the distance vector Ri of each cell I from its center to the axis of rotation. Then the absolute velocity becomes this one, which includes the rotational effect. Then this u vector is substituted into the Navier-Stokes equation, which generates extra terms. I'm not going to dive into this and explain everything in detail because we don't have time for that. But a single set of equations is solved at the end of the day with rotational source terms added only to the rotating zone cells, as you can see here. U and UR are they appear under the same divergence operation. So it is an uncommon practice in CFD. So this is treated with phase flux correction. The full derivation can be seen in this link. You can check it. Velocity at the boundaries within the rotating frame is corrected also. So if you have some ball boundaries or any other boundaries within the rotating frame, the solid body rotation is satisfied by correcting the velocity at the boundaries. Okay, so let's move on to the simulation demonstration. So I would like to open up my terminal here. Can you see my terminal, hopefully? Here.
Yes.
And, so we can connect to the Truba server. Okay, I'm on Linux, by the way, but it doesn't matter. It should be similar in Windows or Mac, I guess. So you can connect to the Truba server using the SSH functionality. My username is Önel, so I'm going to connect to the Levrek1 machine here. I enter my password, and now I'm connected to the Truba server here. I can print my working directory, and you can see I'm in Truba home Önel directory. Okay, I can also mount my Truba home directory to my local machine. How I can do that? I can use sshfs command. I'm not going to write this, but instead I have a function for that. I have Truba mount, or was it mount Truba? Okay, is it mount Truba? I can write mount Truba. I can enter my password. So what I did here is I mounted this directory in the remote machine in Truba to my local directory here. So this is my local terminal. I can go to my home AE Truba directory and I can list the documents here. So you can see these documents. These documents are actually located in the remote server, but they are mounted on my local server, local machine. So how can you use OpenFOAM in Truba? OpenFOAM is already installed in Truba servers. You can change your directory to here and see the OpenFOAM versions. There are several OpenFOAM versions installed, I guess, OpenFOAM 6, 8, 9. We are going to use OpenFOAM 8 for this demonstration. And also the Truba server uses a SLURM workload management manager. What it does that many people use Truba, right? So everyone submit their job and get into a queue, and this SLURM workload manager manages when everybody's work are going to start or end. So you can get a job script here also. Actually, we can check it. We can go here and let me see. I can write nano Truba SW Santos 7.3 app OpenFOAM and OpenFOAM 8. Oops, sorry, OpenFOAM 8 SBatch. Yeah, you can see the file here. This is located in the remote server. You can write here which queue you are going to use. The Truba has many different queues. You can check them on their website. Your username, your job name, how many cores you are going to reserve, and what is your workload time, and stuff like that. And there are many more. Some modules are loaded, some environmental variables are defined for OpenFOAM to work properly, but I'm not going to go into them. You can use this as a template for your job script. And you can go to the okay, let me change directory to my home directory. In your home directory, you have a file named bash profile. So this bash profile file works like that. Whenever you log into Truba, everything written here is automatically executed. For example, whenever I log into Truba, these modules are loaded, C compilers, OpenMPI libraries, and I have some functions, as you can see here. If this OF8 function does everything necessary for OpenFOAM version 8 to work properly. It loads modules, it exports some variables, it defines some paths and stuff like that. I just defined this. So instead of writing them all one by one, I can just write OF8. And everything is loaded from OpenFOAM 8 library. So I can use any OpenFOAM command. For example, block mesh or incompressible solver, IcoFOAM. Anything I can use now, you can see. And finally, we can go to our case directory, which is located in OpenFOAM, Önel 8, and VAWT 2D. So the good thing about mounting this directory to my local machine. So this is home versus AE. You can see this one. This is my local directory in my local machine. AE Truba. So when I go into Truba, the folder looks empty, but let me refresh this browser by hitting F5, and you can see the files on the Truba server on my local machine. So I can manipulate files easily here. I can open them with my local text editor, and it is very easy to use. Okay, let's move on to our solution, our test case. So we are going to replicate the work from Abdulrahman et al. The solution domain looks like this. We have an outer domain. We have an MRF domain defined here. So there is an interface here. So this frame is going to rotate. It's not going to actually rotate, but this domain will be manipulated to present rotation. And we have three blade sections. So this is a fully 2D simulation, right? So rotor radius, number of blades, the blade profile, NACA 0018, the chord length, pitch angle. You can see the details here. And simulation details are U infinity is 10 meters per second. This is an incompressible simulation. So pressure is, gauge pressure is 0 everywhere in the far field. The turbulent intensity is 10% at the inlet. And we are going to use K epsilon turbulence model so that we can obtain the solution quickly. And K and epsilon values at the inlet boundary is calculated using these functions. At the outlet, zero gradient boundary condition is applied, and at the upper and lower boundaries, symmetry boundary conditions are applied. So they are similar to zero gradient boundary conditions. Okay, so I would like to show you the structure of an OpenFOAM case. So we can go to the VAWT 2D case using my file browser, local file browser, and we can also see it here. Let me see, where am I? Okay, I'm also here. You can see all clean, all run as patch, the same files here. Nice. So what does each of these items do? So zero directory, which is not yet which does not yet appear here. It is actually hidden in my stuff directory, which I usually store everything related to not related to me, not going to be used by OpenFOAM yet. So this zero ORIC will be copied into the main working directory later. But let me explain. Zero directory includes all initial conditions for U, P, K, and epsilon, all of the field variables. So we are solving a K epsilon, we are using K epsilon turbulence model, right? So we have U, velocity, pressure, turbulent kinetic energy, anticipation rate field variables. So all initial conditions are defined here. So let us just open one of them. For example, U. So at the inlet, we have a fixed value boundary type, and it has the value of internal field, which is defined here, internal field, uniform, 10 in the x direction, 0 in x, y, and z directions. Same goes for P, K, and epsilon. At the outlet, U is defined as 0 gradient. So this is how you define boundary conditions in OpenFOAM. In the constant directory, we have MRF properties, for example. MRF properties includes what the MRF zone is going to do. For example, it is going to rotate around this origin, around this axis, with this omega value per radians per second. Turbulence properties. It defines the turbulence model. Simulation type is Reynolds average Navier-Stokes equations, and a K epsilon closure model is used. Okay. Transport properties. The fluid is Newtonian, and its kinematic viscosity and density are given here, and so on. In the system directory, you have the controlDict. These are dictionaries. Ata explained for SU2, right? So these are the configuration files for OpenFOAM. They are separated into numerous files, unlike SU2. But in the controlDict, you can see, I hope these are clearly visible to you. We are going to use the simple form solver. We are going to start from latest time, which is going to be 0. And we are going to stop at end time, which is defined as 50,000 iterations. Delta t is 1. And we are going to print out at every 100 time steps. And you can define custom functions here. For example, I'm going to use y plus function, which will print the y plus value, which is going to calculate y plus values and going to print them. So I load necessary libraries for that and write down the necessary definitions here. And also I'm going to calculate forces, because at the end of the day, we are interested in forces, right? What is the moment, torque? What is the forces in x and y directions, drag, for example. So I define rho infinity as 1.225 because we are simulating air. You have to define this because in OpenFOAM's incompressible solver solves equations per density. So it solves equations independent of density. And center of rotation is defined here. Okay. Let's move on to, for example, decompose PARDICT. This defines how the solution domain is going to decompose. So we have our solution domain here, right? So it is going to divide this solution domain into simply 4 domains, 2 in the x direction, vertical, and 2 in the y direction. So we are going to obtain 4 domains at the end of the day. Okay. And fvSchemes and fvSolutions, solution files. These are very important. fvSolution defines which algorithm you are going to use to solve pressure equation, to solve velocity equations, K equation. And also you define the convergence control here. For example, our solution will converge when the residuals drop down to 10 to minus 6. And you also define relaxation factors here, which is necessary for simple algorithm to work. A simple algorithm works with relaxation. So if your simulation is diverging, you may try lowering these values. This doesn't affect the final solution, but it affects how you reach the final solution. Lowering these values will make your solution more stable, but it will take more time to finish. Okay, what else? Polymesh. We don't have the Polymesh file yet. It is again hidden in my stuff directory here. It includes all the mesh, it includes the mesh file, the solution grid, and necessary definitions here. There is too much to talk about, so I'm going to skip, but the boundary, phase data, cell neighbor data is all stored here. So I've generated the mesh beforehand. I'm going to show you the mesh. It's all here. And this all-run SBatch, this is the file we are going to submit to the SLURM workload manager, right? So the SLURM workload manager will check these parameters, and it is going to get this job to the METU queue with these parameters, and it's going to execute the job. So what do we have here? Account Önel. This is my account name. This is the job name, VAWT 2D. We don't have reservation. This is unnecessary here. Okay. So we are going to get 4 cores for our parallel simulation, which is consistent with our decompose par definition. We are going to partition the domain into 4 subdomains. We are requesting 1 hour of workload time. It is even, we don't even need that much time. It's going to finish quickly. If you want, if your job is going to, if your job takes too long, you can ask SLURM to send you an email when your job is done. You can define your email here. And everything, every output will be written in the SLURM out, and every error will be written to the SLURM error file here. Not here, but here. Okay. So as I mentioned, first I source, the job manager will source my home, my bash profile. It will load every module necessary, and it will source, it will load the environmental variables for OpenFOAM using this function. If you remember, this function is defined in my bash profile file. So it will load some necessary run functions from OpenFOAM libraries. For example, by loading this, you can use run application and run parallel functions to run your OpenFOAM applications. Okay, so this two-line will simply copy my stuff 0oric, this one, this file, into the case directory as 0. So this will just copy this directory and paste it to the case directory as 0. And similarly, it's going to copy my mesh as polymesh into constant. And it is going to first decompose the domain using decompose par application. Then it is going to run application in parallel. So what is application? This is a feature of OpenFOAM. Oops, sorry. So this run parallel application will go to, will go to system. It is going to check system controlDict, and it will get this application, and it will see the OpenFOAM text here, and it is going to run OpenFOAM. So if you change your application from simple form to pimple form, for example, it will automatically run pimple form. Okay, so I guess everything is clear. So let's move on to running our simulation. I hope we have time for that. Okay, so let me first see where I am. Print working directory. So I'm located in the correct directory, VAWT 2D. So what I have to do is I've made everything ready beforehand. I will just submit my job to the SLURM workload manager. For that, I can use sbatch all run sbatch. So this will effectively submit all run sbatch file. Let's hit enter. Submitted batch job with this ID. So you can see how is your job is doing in the queue. For that, you can execute the sq command. Okay, so it says it is running. R means running. It is running in the Barbun 48 node list. Okay, so if I refresh my local file manager F5, you can see that some stuff is going on here. First of all, the decomposed par application of OpenFOAM has divided the domain into 4 subdomains. Each one is stored in processor 0, 1, 2, 3. And it also writes the functions I have defined in controlDict, which are y plus, forces, and residuals functions into post-processing. You can see here, forces are written here, residuals are written here, and y plus is written here. So using the, let me clear this, using the form monitor application of OpenFOAM, in log scale, I can plot the residuals live. How can I do that? Oh, sorry. First, I have to change my directory to OpenFOAM, Önel 8, and VAWT, this working directory. Now I can use foam monitor in logarithmic scale, show me the residuals. Yeah, so you can see here how our residuals are converging, right? So if we wait for some few seconds, you are going to see that this graph is updating itself every 5 or 10 seconds, I guess. So you can see here that residuals for P, velocity K, and epsilon are dropping, and they are going to keep dropping until the convergence criteria is reached. So what is our convergence criteria? It is defined in the fvSolution file. It is 10 to minus 6. So there's a good thing with OpenFOAM. We can change these values on the fly, and OpenFOAM is going to accept the changes. So if I change this convergence criteria to 10 to minus 5 and I save this file, solution will most likely stop because 10 to minus 5 is already satisfied. So let me save this file and let me check the job queue. You see, the job is terminated because OpenFOAM, the simple form solver, checks fvSolution file at every time step and checks for any changes in this file. If there are any changes in this file, it is immediately reflected into the solution. So this is provided by this definition in controlDict. Let me see it. Let me find it. Runtime modifiable. If you make this true, what I've explained works. If you make this false, it doesn't check anything during runtime. So whatever settings you have defined at the beginning persists throughout the simulation. Okay, so we have a solution, right? So we can check the solution by using ParaView, which Ezgi has explained in detail previously. I have a state ready here. What is a state? I have saved my ParaView screen to show you previously. I'm just going to load this. Okay. So this loading is most likely, it is going to take some time because actually my local machine is getting data from the Truba servers right now in the background. This is why it takes some time. Okay, I hope everything will work fine. Okay, let me go to the final time step, to the final frame. So this is our final, oops. This is our final solution frame. You can see here that the streamlines are deflected due to the rotation of this frame MRF zone. Actually, I can show you the MRF zone like this. So this is our solution domain. This is the inlet on the left, outlet on the right. We have this MRF zone. If you can see it, there is a circle, there is a fine circle here. So all of the cells within this domain, within this zone rotates. It doesn't rotate, but it simulates rotation. And we have our airfoils here with boundary layer mesh around them. And you can change this color to U to see the solution. Okay, so we have a solution, and what else we can do? We can check the forces, right? So I can go into forces. How I can do that? Go to post-processing, forces dot. Okay, so is this visible? Hopefully this is visible. So it writes forces, pressure, viscous, porous, and moments, pressure, viscous, porous, like that. So this part, yes, this part contains forces. So this is the this is the force in the x direction caused by pressure effects, y direction caused by pressure effects, and z direction caused by pressure effects. So z direction is effectively 0. 10 to minus 19 means 0 actually, because this is a 2D simulation. And similarly, viscous and porous. Porous, we don't have some porosity in our simulation, so it is 0. And similarly, moments. You can see the moments here. So just let's just go down to the converged time step. In the final time step, in the final iteration actually, we have so we are interested in the moment around the z direction, right? So we are interested in the last component of the moments, this one and this one. Actually, if you check, moment around x and y directions are effectively 0 again, 10 to minus 18. So these two values are the ones we are interested in. This one is caused by the pressure effects. This one is caused by the viscous effects. But at the end of the day, we are interested in summation of these two, right? So I have written a simple MATLAB script. I will going to run it in Octave, actually. Let me see. Let's go to my stuff. Okay. So, oops, sorry. Can you see this? Hopefully.
Yes.
Okay, so this just calculates the power coefficient. I'm not going to explain it in detail. I'm going to go into my stuff directory, and I'm going to run Octave, and this pressure and viscous forces, we can get these from also we can get this from log simple form. Okay, sorry, we can't get them. Okay, from here, we can just copy these values. There are more elegant ways to do that actually, but let's just do it quickly. So these two are the momentum pressure and momentum viscous. So we are going to sum them up and calculate the CP. I will just run power. So tip speed ratio is 2, and our power coefficient turns out to be 0.28. So let's compare this to the reference value. Let's discuss the results. So the paper from Abdul Rahman finds the reference value, finds the CP by 0.29. In my previous run, I have found it as 0.25, but now that I have allowed to residuals to drop further down, the relative error is even less, right? So we are very close to the reference value. But these results does not mean these results are true. So there are some questions to ask here. First, does multiple reference frame really reflect the physics of the problem? It is worth checking the method's sensitivity to radius of the rotating zone. So the radius of the rotating zone is defined as that. But what happens if this is smaller or larger? This could be investigated. And also, position of the turbine. What if we didn't put this plate here, but here? What if we rotated this turbine geometry by 30 angles, for example. Are we going to get the same result? This could be checked. How well do the K-epsilon model and its wall functions work? So we should also check the y plus value. So the first cell should be located here when you are using a wall function, right? The fully turbulent log-law zone. So we can also check the y plus value. We can go to post-processing, y plus 1. And we can check the, as you can see, the minimum y plus value in our simulation around the walls is 16 and the maximum is 80. But we know that putting your first cell well below the viscous sublayer or within the buffer zone would yield erroneous results, right? So the first cell should be here, around here. So what we did was a not good practice, but this is just for demonstration purposes. So this should be also checked. Is the mesh good enough? We didn't check the grid convergence. And also we have only used first order schemes in this simulation. You remember the FV, too many things on my screen. Let me check this. Yeah, in the system directory, FV schemes, these are the schemes we have used for divergence, gradients, and stuff like that. So Gauss upwind is a first order scheme. It is very stable. It converges really fast. I've used this for demonstration purposes, but this doesn't yield correct results. The results in ParaView may look correct, but actually it is not. So these should be checked. And finally, the simulation should be run at different tip speed ratios also. We are just on time, I guess. Thank you for your attention and hope you have learned something new.
Yes, thank you, Hüseyin. Very good job. Right on time again. Thank you. Actually, I had a question. You showed the residual plot. You run it on your mounted
Yes.
directory, and how did it work? I mean, we saw the GUI. So is it working on your computer or on Truba?
Hocam, it runs on my computer because as far as I know, Truba doesn't have an X server, so you cannot get visuals from Truba. I might be wrong, but I couldn't manage
Yeah,
that.
you need to open the X server to be able to see the GUIs
Yeah.
from Truba. If you didn't do that, yeah, but
If
when
you
you run,
if you run FOAM monitor in Truba,
Mhm.
if you were able to do that, Truba will just send you the visual. It will just send you the visual only. But if I run it on my local machine, it will load the data, load the raw data from
Okay.
Truba server in the background. You don't see it, and render the image on my local machine. So the thing is, if this y plus data is just 4.1 kilobytes, but if this were, for example, 1 gigabyte, if this was 1 gigabyte in size,
Yeah,
it will take a
takes time.
much longer time. Yes.
Yeah. So when you run monitor that function,
Hocam, this function,
I mean, is it on your system? Does it see your system? So which
it is on
function?
my system. It is on my
Okay.
system. I'm
Okay.
using the OpenFOAM installed on my. Actually,
Also.
I have opened this using OpenFOAM 9 because I have
Ah,
OpenFOAM
okay.
9 on
Yeah,
my
that
system.
was my question. Okay.
Yeah, yeah. And I was running OpenFOAM 8 on Truba, but
It it should give the
thankfully,
same. Yeah.
yes, thankfully we don't have much version differences between these two, so it is
Okay.
easy to just open.
Great. Thank you.
You're welcome.
I don't know if any other questions we have. Okay. Maybe I can also ask, did you check the scalability for OpenFOAM? I mean, maybe we can make a comparison of SU2 and OpenFOAM using the same grids on Truba to compare the performances of the codes. I think there is
Yes.
that was one question. Yeah.
Hocam, actually, I have an idea of comparing SU2 and OpenFOAM in terms of both scalability and Ata has mentioned the compressibility effect, right? The tip
Yes.
reaches Mach 0.2. This is very interesting because I would also like to see how the results,
Yeah.
what results do we obtain using an incompressible solver and a compressible solver. That would be an interesting case to observe.
Yeah.
Maybe
Yeah.
Ata and I
You
may
can, yeah.
run the same simulation with SU2 and OpenFOAM, maybe.
Yeah, that's a good idea. Thank you. We will do that, hopefully.
Okay, hocam.
Okay. If you have, attendees, if you have any more questions, you can always, always ask later on also. So you can reach us anytime.
I had to rush a little bit because there are so many things to talk
Yeah,
about
sure.
from zero to simulation on Truba, but
I
I
think you covered
skipped.
very well. Yeah,
Thanks, hocam.
it was very clear, and it will help for the beginners and for the advanced students as well. They can, if
Hopefully.
they already know, they can apply this test case easily. Hopefully, we will provide the sample files so you can try by yourself.
Sure.
Yeah, great. Thank you very much.
You're welcome.
So I think we have a break now.